Welcome to section 11.4, limits of a sequence, and this is going to be our final set of notes for this year, so you've made it, congratulations. We're just going to go ahead and continue on with this idea of limits at infinity. So when we're trying to do the limits of a sequence, it's basically what we're doing. So we have the limit, don't need the blue pen. We want to do the limit as, and our variable this time is n. So the limit as n approaches infinity of 2n plus 1 all over n plus 4. I'm going to do the exact same idea here. I'm going to take a look at the degree. So if I say the degree of the top is going to be 1, and the degree of the bottom is going to be 1, that means that these guys are going to basically grow at the exact same rate, the top and the bottom. The only difference is what they get multiplied by, which is their leading coefficients. So since I see 2 and then there's nothing in the bottom, I know I can just kind of slide a 1 in there as the leading coefficient, then I know that the limit as n approaches infinity of these is just going to be 2. Since this is actually approaching a unique number, 2 is a unique number, then I would say that this limit converges. So therefore, it converges. That's because it's going to a unique value. All right, 8. So why don't you pause here? This is just like what we just did in the previous notes. Go ahead and do the limit as n approaches infinity of this. Compare the degrees. See if you can figure out what value it's going to go to, and then determine if it converges or diverges. Okay, so went ahead and put in my limit notation. I compared the degree of the top and the bottom. The degree of the bottom is larger, which means the denominator is going to grow faster. When the denominator grows faster, it becomes a larger number than the top, which means I get a small fraction. And a small fraction gets really super close to 0. So my limit is going to be 0, and because it's going to a unique number, it converges. And our last one for the notes. I'm going to do the same idea. Now we have factorial here, so we got to remember what that means. So we're going to do the limit as n approaches infinity. And n factorial, remember, it's the idea of the value times the previous integer value. So we've got n, the previous integer is always going to be 1 less, and then 1 less. Oh, let's go back to that. My apologies, that should be a 2. And then 1 less. Now, since I don't know what n is, this goes on and on and on forever until I get down to the actual value of 1. Likewise, let's do the same with the bottom. So I'm going to start at n minus 1. The previous value, subtract 1. The previous value, subtract 1. The previous value, subtract 1. Dot, 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 all the way down to 1. Notice that we have this nice little pattern here. You'll see that starting at n minus 1 and working all the way down to 1 completely matches up with the bottom. So let's go ahead and use our techniques for algebraically manipulating limits or evaluating them. We can just cancel that business out. Anything that matches top and bottom. Now there is going to be an n minus 4 there, and then those 1s are going to end up canceling as well. So it looks like we have the limit as n approaches infinity of just n. Now, we are talking about the top of a fraction, so we can put a 1 in the bottom there. So it looks like the top of this fraction is going to completely blow up, which means it's going to approach infinity. Therefore, I would say the limit, and I canceled a whole bunch of stuff out, so let's just rewrite this. The limit as n approaches infinity of n factorial all over n minus 1 factorial is going to give me infinity. Therefore, limit does not exist. Therefore, I would say that it diverges. It doesn't approach a single unique number.